Good morning everybody. I am Professor Muhammad Wasim Akram. Welcome to all of you in my video lecture series. I have been teaching this course for the last 12 years. These video lectures will be very useful to the students of civil engineering. So keep watching, like, comment, share and subscribe our channel. Thank you. Good morning students. In the last class, we learned about the consistency of clay. Consistency is the relative ease with which a soil can be deformed. In practice, the property of consistency is associated only with fine-grained soil, especially clays. Consistency is a term which is used to describe the degree of firmness of soil in a qualitative manner. The boundary water content at which the soil undergoes a change from one stage to another are called consistency limits. In 1911, a Swedish scientist, Atterberg, first introduced the significance of these limits, and they are also known as Atterberg limits. These limits are liquid limit, plastic limit and shrinkage limits. In the last class, we learned how to find these limits in the laboratory. So this is just a quick revision of the last class. Remember, liquid limit and plastic limit indicate the plasticity of the soil, whereas the shrinkage limit is useful for expansive and shrinkage behavior of the clay. This liquid limit and plastic limit of soil are dependent on the amount and type of clay in the soil. Now moving to the next topic, that is called plasticity index. Plasticity index, symbol is IP, the range of moisture content over which a soil exhibits plasticity. This is the difference between the liquid limit and plastic limit. Remember, plasticity index indicates the degree of plasticity of soil. Greater the plasticity index, greater the plasticity of the soil. Clay soil possessing high value of liquid limit and plastic limit plasticity index are referred as highly plastic or fat clays, and those with low value described as lean clays. Coarse grained soils cannot achieve the plastic state of consistency, and their liquid limit and plastic limit may be said to coincide, that is, I be equal to 0. When the liquid limit or the plastic limit cannot be determined, the plasticity index is reported as non-plastic. When the plastic limit is equal to or greater than the liquid limit, IP or plasticity index is reported as 0. Here we can see in the table the soil is classified based on plasticity index. If the plasticity index is 0, the soil is called non-plastic. If the soil is plasticity index is less than 7, the soil is called low plastic. If the plasticity index is in between 7 to 17, the soil is medium plastic. And if the plasticity index is more than 17, the soil is highly plastic. Here we can see the plasticity index is seen to be dependent mainly on the amount of clay present in a soil. In this table, it gives an idea of the relationship between the Atterberg limits and the engineering properties. An important indication of the compressibility of soil can be had from the liquid limit of the soil. We can see here, greater the liquid limit, greater the compressibility of the soil. In fact, reliable correlation between the liquid limit and the compressibility parameter are in practical uses. And we can also see for soil with the same value of liquid limit, the greater the plasticity index, the greater the dry strength and toughness at plastic limit, but the permeability and rate of volume change decreases while compressibility remains the same. Another observation is from this table, comparing soil with equal values of plasticity index, it is seen that with an increase in liquid limit, the dry strength and toughness decreases while the permeability and compressibility increases. Now we have another important term, relative consistency or consistency index. It is defined as the ratio of the difference between the liquid limit and the natural water content of a soil to its plasticity index, where WL is liquid limit, WN is natural water content, and IP is plasticity index, that is liquid limit minus plastic limit. From this definition, we can observe if WN is equal to WL, then IC, that is relative consistency, is equal to 0. When WN is equal to WP, that is plastic limit, IC will be equal to. Another term is liquidity index, symbol is IL. IL is equal to WN minus WP divided by IP. It means liquidity index is defined as the ratio of the difference between natural water content of a soil and the plastic limit to its plasticity index. As in the previous formula, we have seen WN is equal to natural moisture content, W2 plastic limit, and IP is plastic limit. If we rearrange this equation, we can see liquidity index is equal to 1 minus consistency index or relative consistency. So this is the relation between liquidity index and consistency index. This table provides guidelines to describe the consistency of cohesive soil using consistency index IC and liquidity index. Here we have consistency, that is liquid, plastic, semi-solid and solid, and the description is liquid, very soft, soft, medium, stiff, stiff, very stiff, and hard or hard, hard or very hard. Based on the value of IC and IL, we can describe the soil like this. Here we can see, it means in case of liquid, if the consistency is liquid, the description is liquid means IC will be 0 but IL will be more than 1. In case of plastic consistency and the soil is very soft, then consistency index is 0 to 0.25 but liquidity index will be 0.75 to 1. For soft soil, liquid consistency index will be 0.25 to 0.5 but liquidity index will be 0.5 to 0.75. For medium stiff, consistency index will be 0.5 to 0.75 but liquidity index will be 0.25 to 0.5. For stiff soil, the consistency index will be 0.75 to 1 but liquidity index will be 0 to 0.25. Sorry. If the consistency is semi-solid, the soil is very stiff or hard, consistency index will be more than 1 but liquidity index will be less than 0. For solid consistency, hard or very hard, the consistency index will be more than 1 but liquidity index will be less than 0. Liquidity index and relative consistency are good indicator of consistency of the soil. If the liquidity index is less than 0, the soil is likely to behave like a brittle solid, that is a brittle fracture will ensure when sheared. Here we can see these three figures A, B and C. A liquidity index is less than 0. Here in figure B, liquidity index is in between 0 to 1, and in figure C, liquidity index is more than 1. We can see here when liquidity index is between 0 to 1, the soil will behave like a plastic, and stress strain response may vary between the shape of two curves shown in the figure B, depending on where the natural water content scales in the plasticity range. If liquidity index is more than 1, then stress strain behavior is similar to that of the viscous liquid as shown in the figure C. Such a soil may virtually flow like a liquid, but only when upon disturbance. If left undisturbed, it is quite capable of withstanding significant load owing to the structural bonds that are intact. Once these bonds are broken on account of any disturbance, the soil is incapable of sustaining any load. Another term is flow index. Flow index is the slope of the flow curve obtained between the number of blows and the water content in a Casagrande test for determination of liquid limit, as we have seen in the previous lecture. Here we can see in this figure, here in the figure also, the flow index is nothing but the slope of the flow curve. The flow index indicates the rate of loss in shearing strength upon increase in water content. A soil with higher value of flow index possesses low shear strength when compared to a soil with lower value of flow index. Another term is toughness index, IT. It is defined as the ratio of the plasticity index to the flow index. Toughness index gives an idea about the shear strength of the soil at plastic limit. Remember, two soils having the same plasticity index value possesses toughness which vary in inverse proportion to the flow indexes. It is therefore quite clear that different soil have different shear strength at plastic limit. IT, that is toughness index, generally lies between 0 to 3 for most soil. When IT is less than 1, the soil is friable. It means easily crushed at the plastic limit. Now the term shrinkage ratio. Shrinkage ratio is defined as the ratio of a given volume change in a soil expressed as a percentage of the dry volume to the corresponding change in water content above the shrinkage limit. Here we can see V1 is volume of soil at water content W1, V2 is volume of soil at water content W2, Vd is volume of dry soil mass. If we rearrange this equation, the shrinkage ratio can also be written as gamma D by gamma W, where gamma D is unit weight, dry unit weight, and gamma W is unit weight.